Okay, so this brings us to our next example, and this is a pretty loaded example, so I'm just going to read it out loud here. For each of the following functions, we'd like to know whether or not the function has a limit at the stated a values. We're going to use a numerical and algebraic approach to investigate, which basically means we're going to use a table of values and we're going to use algebra to figure this out. And if possible, we're going to estimate or determine the value of the limit. We're going to compare the results with a careful graph of the function on an interval containing the points of interest. So in this next example, we're doing all three ways to calculate a limit. We're going to use a table of values, we're going to go with algebra, and then we're going to verify everything by looking at the graph. So the first function that we're going to look at is f of x equals 4 minus x squared over x plus 2. And specifically, the a values that we want are going to be at a equals -1 and a equals -2. In the third part of the video, we're going to look at g of x, which we'll talk about later, but that's going to be our next function at a equals 3 and a equals 0. Okay, so let's start with this first function, and specifically, let's start with a equals -1. So if we take a look at the graph of f of x, believe it or not, the graph of f of x is actually a linear function, but it's a linear function with a discontinuity. There's a hole in the graph, and if you remember back from your pre-calc days, and this course is not about graphing functions, but this numerator can be factored. And when we factor the numerator and go through all that rigmarole, we find that there's going to be a common factor of x plus 2 in the numerator and denominator, which tells us that there's a hole in the graph at -2. So that's why the graph of f of x looks like this. So we'll just keep that in the back of our mind. But it specifically asks us to use a table of values to do this. So what we're going to be doing is we're going to let x, which is equal to a, we're going to let x equals a, which equals -1. X is going to approach -1, and we're going to approach -1. If you look over here on the graph, we're going to approach -1 from both sides. We're first going to approach it from the right-hand side. So we're going to start out at -0.9, and then we're going to get -0.99 and -0.999, which is really close to -1. But then we're also going to do it from the left-hand side. So we're going to say -1.1, -1.01, -1.0001. So we're getting infinitely close to -1 from both sides. And when we do this on a table of values, which we discussed in class, on how to do this on your calculator with a table of values, we can see that, and I'm going to highlight this line right here, as I get infinitely close to -1 from the right-hand side, the output is approaching 2.99999, which we're just going to call 3. And I'm going to look at this value down here. As I get infinitely close to -1 from the left-hand side, the output is approaching 3.0001, which we're going to call 3. So as long as we see that this value and this value match, or are pretty darn close to each other, then it's safe to assume that there is a limit as x approaches -1 of f of x, and that limit is going to be 3. All right, now if you look at the graph supports that, right? At -1, I get really close to 3. In a table of values, I'm showing 4 values on each side of -1. I'm going to say when you use a table of values on your calculator, you need to show 3 values leading up to -1, in this case, on both sides, 3 values to establish the pattern. Okay, so the table suggests that the limit as x approaches -1 is equal to 3, so that's a good thing. The graph supports that. And so now we're going to look at this from an algebraic standpoint. Let's do some algebra with this thing. And when we do the algebra, we're going to consider the numerator and the denominator in separate cases. All right, so the first thing we're going to do is we're going to say, okay, let's let x approach -1 of 4 minus x squared. Well, the thing is, 4 minus x squared is a continuous function. All right, just in and of itself, 4 minus x squared is continuous. There are no restrictions on 4 minus x squared. So because there are no restrictions, I can get a sense of how this thing is behaving. I can simply just plug -1 in for x. It's a little bit of a cheat, right? We're kind of cheating the system a little bit, but because it's continuous, we can do this, and we find that when we evaluate this, we get an answer of 3. Well, that's good news, because that's what we saw earlier on. And now I'm going to take the same thing in the denominator. X plus 2 is a continuous function. It has no restrictions to it. Okay, in and of itself, x plus 2, just a linear function with no restrictions. So I can cheat a little bit, and I can say, okay, let's just plug -1 in for x, and when I plug -1 in for x, I get 1. Okay, but now what we do is when we put the numerator and denominator together, now we can say the limit as x approaches -1 of f of x, there's the argument, is equal to 3 over 1, which is equal to 3. That's good news because that's what the table suggested, and that's also what the graph suggests. Okay, so at this point, let's move on to a equals -2. We're going to start with the table of values. We're first going to go from the right of -2, so we're getting closer and closer to -2 from the right. So -1.9, -1.99, -1.999. We need 3 values here to establish a pattern. We see that this thing is approaching 4. Okay, so this is the line that I'm most concerned with. It's actually this one down here, but again, in this table, I'm using 4 patterns. We could use 3 and be just fine. Then I'm going to approach -2 from the left. So -2.1, which is somewhere around here, -2.01, -2.001. This is also approaching 4. Okay, so that's good news because they're both hovering around 4. I look at my graph and I go, yep, even though it's undefined at x equals -2, I'm getting as close as I want to -2 without actually touching -2, and it does have an output of 4. So that's a good sign. All right, so the table suggests that the limit as x approaches -2 of f of x is equal to 4. The graph supports this, and so now we're going to do this from an algebraic standpoint. So here we go. The problem here is f of -2 is actually undefined. All right, f of -2 is undefined. And if we use this same strategy, let's just try this. If I take the numerator, which is a continuous function, and I do the cheat, and I say because it's continuous, I can put in -2. When I evaluate 4 minus a -2 squared, that ends up being 0. That's interesting to me. Well, we'll see why in a second. When I do it in the denominator, x plus 2, it's a continuous function. I can plug -2 in. I also get 0. Well, Houston, we got a problem here because now when I put the numerator over the denominator, I get the limit as x approaches -2 of f of x is equal to 0 over 0. That's not what we saw in the table. In the table, we were getting a value of 4. So 0 over 0, you might remember this from your pre-calculus days. It's what we call an indeterminate form. And we're going to talk more about an indeterminate form next week, but basically this tells us we have more work to do. We can't just leave it here. So we're going to have to come up with a new strategy algebraically to do this. And so the strategy looks something like this. As I take the limit as x approaches -2 of f of x, which I can substitute in this function, 4 minus x squared over x plus 2. The nice thing about this, as we mentioned earlier, is 4 minus x squared is actually factorable. So I get 2 minus x times 2 plus x. It's the difference of 2 squares. And because of that, my x plus 2's can now reduce. So here's the deal. When we're taking the limit as x approaches -2, the values are extremely close but never equal to -2. So the quotient, 2 plus x over x plus 2, really has a value of 1 for every possible value of x. Think about that for a second. Plug in any x value to this expression, and it will always come up with a value of 1. And therefore, these reduce. That's why we can reduce these. So in that case, we can say that this, and I can't get that black bar out of there, so I'm just going to leave my mouse alone. If you look at the bottom of the screen, we say the limit as x approaches -2 of 2 minus x times 2 plus x over x plus 2, there's our argument, is equivalent to the limit as x approaches negative 2 of 2 minus x. And that's a good thing because now when I take the limit as x approaches negative 2 of 2 minus x, that's a linear function, it's continuous, I can plug negative 2 in for x, and I get 2 minus a negative 2, which is in fact 4. Good news, because that supports the table, that also supports the graph. And we're going to look at the next function in the next video.